Hello everyone. Let's start with a simple observation. In a resistor, voltage and current are perfectly in phase, they rise, fall, and reach zero together. But the moment we bring in an inductor or capacitor, things change. Suddenly, voltage and current don't match step for step anymore. So how do we represent this difference clearly? That's where phasors come in. A phasor is like a geometric tool, a rotating arrow, that helps us visualize both the amplitude and the phase of AC quantities. With phasors, the messy world of phase differences becomes simple and intuitive. Students, let me ask you something fun. When you watch the hands of a clock going round and round, do you ever think of them as creating waves? Well, in physics, that's exactly the idea behind a phasor. A phasor is nothing but a rotating vector that spins with a constant angular speed, omega. Now here's the magic. If you look at its vertical projection as it rotates, it traces out a sinusoidal variation with time, just like an AC waveform. For example, the voltage phasor has a length equal to the peak voltage, Vm. Similarly, the current phasor has a length equal to the peak current, Im. Both of these vectors, while rotating, carry two pieces of information at once, their amplitude and their phase. As you can see in the diagram, the phasor keeps rotating, but the vertical projection on the y-axis perfectly matches V of t equals Vm sine omega t. This is how phasors make our life easier. They take the complex motion of sine waves and represent them as simple rotating arrows. So here's the quick insight. Phasors are like a secret code. They combine both amplitude and phase into one elegant picture. That's why engineers and physicists love them when analyzing AC circuits. Students, let's now connect the dots between phasors and the sine waves we see in alternating current. Imagine a phasor, that rotating arrow we just learned about, spinning at a constant angular speed, omega. Now, if we watch its vertical shadow or projection as it rotates, something amazing happens. It traces out a sine wave with time. The vertical projection of the voltage phasor gives us the instantaneous voltage, V of t. Similarly, the vertical projection of the current phasor gives us the instantaneous current, I of t. As the phasor keeps rotating smoothly, these projections rise and fall continuously, generating the sinusoidal curves we know so well. In fact, every AC waveform you see, voltage or current, is nothing more than the vertical projection of a rotating vector. Look at the graph here. The phasor angle omega t corresponds perfectly to the point on the sine wave. This shows us the deep connection. Rotation in a circle transforms into oscillation along a line. So here's the quick insight. Sinusoidal alternating current is simply the vertical projection of a rotating vector. And that's the power of the phasor method. It transforms wavy mathematics into simple geometry. Now that we understand phasors, let's see how they behave in the simplest AC circuit, a resistor. In a resistor circuit, the voltage phasor and the current phasor always point in the same direction. That means the phase angle between them is zero at all times. No lead, no lag, they are perfectly in step. This also means that in the time domain, the voltage and current curves overlap exactly. When the voltage is at its maximum, the current is also at maximum. When the voltage crosses zero, the current also crosses zero. If you look at the diagram here, both V and I phasors rotate together along the same line. Their vertical projections give V of t and I of t, which match perfectly. This is why a pure resistor is often used as a reference case for AC circuit analysis. It shows the simplest behavior with no phase difference. So here's the quick insight. In resistors, phasor diagrams show no phase shift at all. Voltage and current behave like synchronized twins, always moving together, never ahead or behind. By now, You've seen how phasors help us picture voltage and current in AC circuits. But here's the real power of phasors: they can represent any AC quantity. Mathematically, any alternating current or voltage can be written as a sinusoidal function with a phase. We write it as x of t equals xm sine omega t plus phi. Here, xm is the maximum value and phi is the phase angle. The corresponding phasor is simply a vector of length xm drawn at an angle phi from the reference axis. That means the phasor carries two key pieces of information: how big the quantity is and where it is in phase. This makes life so much easier. Instead of adding or subtracting complicated sine functions, we can add or subtract phasors directly as vectors. That's why phasors are crucial for handling AC circuits, especially when you have resistors, capacitors, and inductors all in combination. So here's the quick insight: phasors beautifully unify amplitude and phase into a single vector tool, making AC analysis simple, elegant, and visual.
So, to wrap it up, phasors are rotating vectors that bring clarity to AC analysis. Their lengths represent peak values, their angles represent phase, and their vertical projections generate the familiar sine waves. For a resistor, the voltage and current phases coincide phase angle 0, but with inductors and capacitors we'll see interesting phase shifts, and phasor diagrams will guide us through. In short, phasors are the bridge between the mathematics of AC and the geometry we already know. I hope this has made the concept of phasors clear and exciting for you. In our next session, we'll apply AC voltage to an inductor and explore how the phase relation changes dramatically. Until then, keep visualizing these rotating arrows. They're the key to mastering AC circuits.